Beneath the world's busiest shipping lanes and strategic straits, under miles of cold, crushing water, the contours of a new kind of naval power are taking shape. It is quieter than a sonar ping and slower than a satellite's sweep, but potentially more persistent than any crewed vessel ever built. The Manta Ray, an autonomous undersea platform developed by U.S. research agencies and naval contractors, is designed to be patient where humans are limited, to hide where men must surface, and to act where the risks of sending people are simply too high. This is not a mere increment in technology. It is a conceptual shift in naval doctrine, from short-term presence to permanent, distributed persistence beneath the waves. Understanding the Manta Ray means grappling with engineering extremes, doctrinal upheaval, strategic headaches for rivals, and deep ethical questions about letting machines operate with lethal or quasi-lethal authority in the underwater domain. The progression from crewed submarines to autonomous systems has been gradual but relentless. The 20th century's diesel, electric, and nuclear boats were revolutionary because they masked movement and allowed nations to project power invisibly. Cold War investments refined quieting, sonar, and nuclear endurance until submarines became the ultimate strategic stealth platforms. But all crewed systems carry logistic tails and human limitations: fatigue, morale, and finite endurance. The idea of an unmanned system emerged first as a force multiplier, a tool to extend the reach of manned assets, and now as a strategic complement capable of doing things crewed submarines cannot: hide for months in confined littorals, host persistent sensor webs, or provide expendable watchers that can be risked where humans cannot. That evolution is what produced experimental platforms such as the Manta Ray, an attempt to take the lessons of decades of undersea warfare and translate them into persistent, autonomous presence. The Manta Ray's hull form and propulsion are intentionally unconventional. Designers borrowed hydrodynamic lessons from large, quietly gliding sea creatures: broad wings for lift and efficient glide, a flattened body to reduce turbulence, and distributed control surfaces that allow subtle maneuvers without noisy thruster bursts. The goal is not to outrun an adversary, but to avoid detection entirely. Low-speed gliding combined with intermittent low-power propulsion minimizes acoustic signatures and thermal anomalies. Internally, systems are modular. Payload bays accept interchangeable mission modules for sonar arrays, communications relays, electronic intelligence collectors, or payload dispensers. This modularity allows the same hull to act as a listening post one month and an interference node the next. Thermal management, shock isolation, and redundancy in electronics are engineered to extreme tolerance because repair is not an option when the platform is months away from the nearest tender. Endurance underpins the Manta Ray concept. The craft relies on a combination of high-energy density batteries, fuel cells, and extremely efficient power management systems. Energy scavenging technologies, wave energy converters, thermal gradient harvesters, or even microbial fuel cells are under-researched to trickle-charge batteries during long hibernation periods. Propulsion choices favor low-noise electric drives or buoyancy-based glide cycles rather than constant propeller thrust. When relocation is needed, short bursts of higher-power propulsion are used, but these are minimized because every active second increases detection risk. Onboard energy budgeting is controlled by mission software. It assesses sensor priorities, decides when to surface for communication or when to remain on the seafloor, and orchestrates battery cycles so that core systems remain functional even after long dormancy. A defining challenge for any unmanned submarine is navigation and decision-making in a medium where GPS does not reach and communications are limited. The Manta Ray therefore combines precision inertial navigation with environmental acoustic mapping and terrain relative localization. Advanced sonar and bathymetric correlation allow the vehicle to recognize its surroundings, matching seafloor features to preloaded maps. Machine learning models help differentiate natural signatures from vessels or other objects, enabling the craft to follow or shadow specific acoustic profiles. Importantly, autonomy extends beyond mere path following. Mission software must engage in target prioritization, threat avoidance, and energy-aware behavior without timely human oversight. The craft must also cope with intermittent satellite links, short, secure bursts that download new mission orders or upload sparse data summaries. This architecture emphasizes local decision authority with constrained, high-assurance overrides from human operators when communications allow. The Manta Ray is primarily an intelligence and persistent surveillance platform, and its sensors reflect that. Low-frequency passive arrays, distributed sonar nodes, and magnetic anomaly detectors create a tapestry of detection capabilities that are difficult to jam or spoof. For more active missions, the platform can field towed arrays, deploy expendable sensor drones, or act as a relay for other unmanned systems. Communications payloads allow the vehicle to form an underwater mesh with sister platforms, extending acoustic communications ranges and creating distributed sensor webs that can localize contacts with much higher precision than a single unit could. In more aggressive configurations, the Manta Ray could carry small, localized effectors, decoys, small-depth charges, or even miniature unmanned torpedoes. But doctrine and legal frameworks constrain weaponization, and many conceptual deployments emphasize ISR over direct engagement. Looking ahead, the Manta Ray concept could evolve into distributed swarms of varied-sized autonomous vehicles. Large endurance platforms could act as motherships, deploying swarms of micro-UUVs to cover vast areas, or to act as sacrificial nodes that confuse adversaries. Improvements in AI, energy density, and underwater communications could enable higher levels of collective autonomy where groups of unmanned craft coordinate their behavior to perform complex tasks. The strategic implication is a future Navy that is less reliant on a few high-value crewed platforms and more on many low-cost, persistent systems that are harder to eliminate en masse. This would change force calculus, making area denial and maritime domain awareness cheaper and more resilient, but also reshaping escalation dynamics in unpredictable ways. The Manta Ray is emblematic of 21st century military change, incremental advances in materials, sensors, and AI combine to create qualitatively new capabilities. It offers unmatched persistence, a new means of undersea sensing, and a platform that can operate where humans cannot. But it also raises pressing questions about how we manage machine autonomy, how we prevent miscalculation, and how we ensure that powerful new tools do not produce more instability than security. The future beneath the waves will be defined not only by technology, but by doctrine, diplomacy, and judgment. If this exploration of the Manta Ray's promise and peril sparked questions, join the conversation. Subscribe for more deep dives into the technologies shaping modern warfare, and tell us which aspect you want next. A focused technical explainer on underwater navigation, a legal brief on autonomy at sea, or a comparative study of global unmanned underwater programs. The ocean is getting more crowded, and the quiet below the waves is about to get a lot louder.